Now, during the plague of 1666, that's not how you expected me to start this video, huh? Cambridge University, where Newton taught physics and mathematics, closed because of the plague. Sound familiar? Yeah, make up your own jokes. But he had to go home to his boyhood home in Woolsthorpe, out in the country in England, and that is where there's a very famous apple tree. I don't know if you heard about Newton and the apple. But if you go to Cambridge also, at King's College, where he was a student and where he taught, there's an apple tree there too that they planted in honor of him. Why is there a famous apple tree at Newton's boyhood home, and why is there an apple tree planted in his honor at King's College at Cambridge? Why? Well, it's because of the old story, which probably is apocryphal, probably not literally true, that he was sitting out in his yard one day, deep in thought. He lived his life deep in thought. And two things were in his field of view. One of them was the moon. Okay, sitting up there in the blue sky, the moon. He thought a lot about the moon. And also there was an apple tree, the aforementioned famous apple tree. And the story goes that he was sitting there looking at this, and an apple fell from the tree, as apples tend to do. The right time of year, they fall from the tree, and that's when Newton got his idea of universal gravity. Okay. Now, I need to stress before I show you this picture that before this, it was believed that the physics down here on Earth was totally different than the physics, or whatever you might want to call it, up above the moon. The orbit of the moon was like a boundary between the terrestrial world and the celestial world. And the physics down here we might be able to know about, where the physics up there was thought to be unknowable and sort of, it just didn't apply. Physics was what happened on the surface of the Earth and not up in the heavens. But when Newton saw the apple fall, he had an idea. Okay, so keep that story in mind. He saw the moon, he saw the apple fall, and he realized that the moon and the apple were the same thing, that they were both behaving according to the same physical law, okay, of gravity. And they were, the only difference between the apple falling and the moon orbiting was accidentals. It wasn't in essence their motion was exactly the same. Here's what was going on. Let's imagine the Earth. The Earth, by the way, is not flat, it is spherical. So there is the spherical Earth. Okay, beautiful. Now let's say we're on top of a mountain. Okay, so there's the mountain, and we're up on top of it. There we are, up on top of the mountain. And we've got a baseball. We're going to throw it. And then let's not worry about air friction, right? Air friction slows things down. But let's not worry about air friction. Okay, we're going to take a baseball and we're going to throw it. So it's going to go like, okay, and land like that. We're going to throw it straight out. So we're going to throw it straight in that direction. So we're going to throw it that way, but the gravity of the Earth, of course, pulls it down. Okay, so that is A. We're going to take it now and do the same thing, throw it in the same direction, directly horizontally that way, but we're going to throw it a little bit harder. Lands further away, right? Big shocker. You throw it harder, it lands further away. Okay, now we're going to give it a really good heave. It's going to land here at C. So it keeps getting further and further and further away. At point A, we threw it gently. Point B a little harder. Point C a little harder. Now we're really going to wing that thing. So it's going to start off in the same direction, but it's going to be pulled downwards like this, and it's going to go halfway around the world before it lands at point D, not E. Getting ahead of myself. Oops, that's a mess. Let's see here. It's going to land there at point D. Now I want to change colors here because I want to show what happens if we throw it really hard. I mean, we just put it in a cannon and we just fire it. Same direction with a greater speed. What Newton realized was going to happen is this. It's going to, like this, come right back around and slap us in the back of the head. Okay. E. Boom! So E is what happens if we really throw the ball hard. It's going to actually go all the way around the Earth. It's going to be curving towards the Earth. Okay, because the Earth is attracting it all the time. The Earth is always pulling it towards its center. So it's going to be attracted to the Earth all the time, but the Earth curves out away from it at just the right rate so that the ball is never actually going to hit the Earth. It's going to zip all the way around the Earth, and if we're not careful, it's going to come around and clock us in the skull. So what we want to do in that case is we want to wing that thing and then get down. And if we wait a little while, 90 minutes, something like that, a little bit less than that, it's going to go back over our head, and it's going to keep orbiting the Earth. Now, air friction will slow it down. We're ignoring air friction. In the absence of air friction, that ball will orbit the Earth, and it will stay orbiting the Earth forever. And that's exactly what the moon does. He realized that orbit E is no different in the orbit of dear old Luna. That the apple falling from the tree, which is what we get, like if we just dropped it, right, we get the apple. It would just fall right to the base of the mountain like that. Okay. So the motion of the moon is responding only to the Earth's gravity in exactly the same way that the apple is responding only to the Earth's gravity. They are the same force. Okay. Now, if we could throw it a lot harder than E, it would go away and never come back. Okay. So, by the way, before I get into this, this is sort of a thematic break. This is why it's called universal gravity, because the gravity that applies to the apple also applies to the moon. And that insight that the physics down on the Earth is the same as the physics that applies up there, okay, was radical. It shattered the boundary between the terrestrial and the celestial. And all of a sudden, the laws up there, maybe we could explain the things that happen up in the sky with the same physics that we use to describe things on Earth. Okay? So that boundary between the terrestrial world and the celestial world was shattered at this point. It was a long time coming, but this is what really did it. The idea that this gravity is universal. And when you see an apple fall, it's the same physics, exactly the same physics as the moon orbiting. But there's a little bit more I want to say here. It goes beyond the moon. Suppose we could throw it even harder, so it takes on a path like this. Okay. We could throw it just hard enough to where it's moving at what we call V sub E, which is known as the escape velocity. If we can throw it hard enough, it will never come back. It won't even hit us in the back of the head. It'll just leave the Earth's gravity and never come back. If that is known as the escape velocity. For the Earth, that's about 11.2 kilometers per second, which is about 7 miles per second. Now that's really fast, right? 7 miles per second, super fast. 7 miles in 1 second. That's basically, from downtown Atlanta to the almost to the perimeter, 285 in a second. Okay. That's going from downtown Decatur to about a mile past Atlanta, downtown Atlanta in a second. So that's pretty fast. But if you could achieve that speed, then the object, wherever it is, whether it's a rocket ship or it's a baseball, will leave the Earth's gravity and never come back. That's known as the escape velocity of the Earth. And if the speed is equal to or greater than this escape velocity, there is no return. The object will never return to the Earth's surface. But if v is less than the escape velocity, it will return. It might take a long time, but it will return. Okay. All right. So we have this yellow orbit here is known as a bound orbit because that baseball is bound to the Earth. The moon is also in a bound orbit because the orbit, the gravity, the motion of the moon keeps it bound to the Earth, right? The moon's not going to leave the Earth anytime soon. It's going to keep orbiting it. It's bound to the Earth, so this is also known as a bound orbit. Okay. But this case here, when we achieve escape velocity or more, that's known as an unbound orbit. So this is the case. Unbound orbit, yeah, that fits in the video. This is the case of a bound orbit. And oftentimes we use the word orbit to describe the motion of something, even if it's not closed on itself. So like the moon goes in a continual ellipse around the Earth. Calling that an orbit makes sense. We all kind of understand that. But in physics land, in astronomy land, even taking an apple and throwing it on the ground, we say that apple's in orbit until it lands. Also, if we shoot an object way beyond escape velocity and it takes off into space, we still say that it's in orbit. Okay, that's a little bit different than the colloquial use of the term orbit, but that's how we use it. So all of these are all bound orbits. Okay. The only one that's unbound in the picture here is the one that's at escape velocity. And if I could go higher than escape velocity, that would also be an unbound orbit. Okay. Let's see. On the moon, so on the Earth, it's 7 miles per second. For the moon, the escape velocity is different for different bodies. VE for the moon is less. It's about 1.5 miles per second. And for the sun, it's very large. It's a strong gravity, requires a lot of speed to escape it forever. 380 miles per second. So the escape velocity varies with the mass of the body. Typically it goes up with large bodies have large escape velocities, require a lot of speed to escape their gravity forever. Small bodies like the moon or maybe an asteroid has a small escape velocity. It requires less speed to escape the motion, the pull of the moon's gravity than it does to escape the pull of the Earth's gravity. And it takes less speed to escape the Earth's gravity than it does to escape the sun's gravity. Okay, that's how that works. Now, I want to say here real quickly, do I have time? No, I don't have time. I'll have to put this in next time. But I do want to say this quickly, that Newton's theory, released in 1687, was phenomenally successful. It solved problems that weren't even problems yet. Okay, it was deeply impressive. And as we go throughout the rest of the class, I will come back to a couple of really great stories about just how impressive Newton's theory was. Okay, just how powerful it was. But these three laws of motion and the law of universal gravitation were just absolutely game changers in the world of science and philosophy. All right, don't forget that. It's one of the truly great accomplishments, intellectual accomplishments in history. So I'll leave you with that. See you next time.